Hello Amiga coders, this is Photon again, continuing with the ASM school for Amiga. As usual my voice is crap, I have no idea. But anyway, let's continue from where we were. This is an illusion, this is the CPU, and what you see is sort of a line moving up and down, but in fact it's just a variable that we increase and decrease, which tells the CPU which vertical raster position to wait for, busy wait for, then change the background color to white, then wait to the next raster line and set the background color to black. So this is essentially how you make effects. You dream up how to make something using what you have available in the hardware. So what you saw there was the system turned off. Now it's turned on. We're back in the assembler. And it shows the most simple copper. All it does is turn off all the bit planes, keep the color burst flag on, and does nothing else. This is the end marker for the copperlist. But now we would like to do the same thing with the copper so that we can use the CPU for other things than busy waiting. And the copper is perfect for this. It has a couple of commands. Basically you have wait and move. This is a wait instruction which waits for an impossible position, and this tells the hardware that the copper list is done and that copper DMA should stop reading the copper list from chip memory. And this is a move instruction. It moves this value into DFF100. That's BPLCon 0 bitplane control register. With this you can do all sorts of fancy things. There's a special wait instruction to wait for the blitter, which I will not show you. I think it's way too early for that. And the move instructions are limited to, let's check that, address DFF 080 and up normally, and by setting copper control to 1 you can reach as low as DFF 040, but you can never change any of the other registers in the custom chip area. So what we would like to do is, first of all, we have a busy wait here, which is sort of, you have to do this if you, this is the wait instruction, the CPU busy wait, the waits to sync for the next frame. Still, we don't want to use it as we're using it now to reset the background color. If we remove this, a semicolon, comments out a line, nothing happens, because after each setting of the background color to white, we set it to black, and this background color continues and wraps around at the bottom and continues again at the top. But the very first frame, the background color down to the white line would have been whatever background color was prevailing in the operating system. And then after the first frame loop, it would have been reset to black. What we would like to do, however, is we would like to set a different background color, and this is the standard starting position for this vertical position, so that we would like to define a nice little screen with a top and bottom thin border. Let's go ahead and do that. This should be left at the top because it should turn off the bit planes the very first chance it gets. And you might as well learn this, because this will make all your, if you have existing sources for Amiga OCS and ECS, your sources might work instantly just by adding this simple instruction. This sets slow fetch mode for AGA compatibility. So this should really be the first instruction of any of your copper lists, unless you want to rule out viewing on any machine that doesn't have OCS or ECS chipsets. OCS would be Amiga 500, for example, and ECS would be Amiga 600, and AGA would be Amiga 1200 and up. Well, I should say Amiga 1200 and those models released later. Anyway, let's set our own background color to start with. Remember, this is the copper starts just after vertical blanking, so that we can set these move instructions. Take 8 cycles each normally, so not much of the frame has been spent since the vertical blank so far. In fact, you can execute 1,000 copper instructions before you reach even this position. That doesn't mean the copper is super versatile or super fast. It's just good at specialized things. And so what we do is we make a move instruction. Remember that all these registers assume this DFF 000 custom base. So you only have to specify the offset. We'll get into that later. And so what we do is we set this to some 0, for example, and not much has changed. What if we change this to middle gray? Well, as you can see, this move instruction in the copper was executed before anything was shown on screen, so that the whole screen from the top where it's executed turns gray right until the CPU butts in and changes it first to white and then to black. And now if we want to have a little bit more fun, we can change it to, let's see, that's a heavenly blue shade, perhaps a little less, whoops, a little less saturation means increasing. These are RGB values and it's too bright, so I'll make that 9. And I have a bug in my keyboard which sometimes double clicks escape for me. Well, that's sort of nice, a bit bright still. That'll have to do. So this is the red value out of 15, or F in hexadecimal. This is 4 out of 15 green value and 9 out of 15 blue value. So to get that thin border I promised, we will have to insert a wait instruction. The way to do this is to type the rasterline number as a byte, as an 8-bit number, and we know that a normal screen starts up here with hex 2C. So let's try that. Actually, we want the screen to start here, So we want the thin border to be outside, and it should be 1 pixel thick. So we subtract 1, x2b. Now for the horizontal position, also expressed as an 8-bit number, this is a half resolution number. That means that for this 320 pixel, or I should say 320 low-res pixel widescreen, 640 high-res pixel widescreen, that would correspond to some value here and some value plus 160 here, because the horizontal resolution is half of that. I happen to know that the horizontal position starts on a raster line at hex position 07 and ends at around hex df. These are the standard values I use. Now, the Windows emulator will show you a little bit more than that if you have a wide enough window. And this is why you see broken copper shades. They have 1 pixel breaks in the right edge here, if you look at old demos, because they've waited for simply hex df or ff and then changed the background color in the right margin in order for it to be ready for the left margin on the next line. So that's the reason for the break. Also, any value less than 0.7 in my experience does the same. So that's the reason for the 0.7 value. And this is the weight mask. It has some special bits and some mask bits that allows you to use the same weight several times in a row. For example, you could wait for every 16th raster line or every 8th raster line, and so on. So this is the wait. It does nothing but let the copper busy wait. Now, that's better than letting the CPU busy wait for this raster line, because it doesn't repeatedly read the memory and check the vertical position like the CPU does, so it doesn't hog any resources. And after this wait, we change the background color again to that plus something, let's say 56B, which is the same RGB value, adding 2 in for each RGB component. Well, that's sort of what we want, and then we want to reset it inside. Control B, Control C, Control F. On the next raster line, I wish to reset it to something dark, let's say, for lack of imagination, well, something like that. So this is our little screen with a thin border. I'll make the border a little bit brighter in the blue department. Okay, that's decent. Now we need to mirror this at the bottom. So then we would have to wait for the very last line. The screen starts at hex 2C and the last line is hex 2B down here, and then line 2B finishes, and hex line 12C after this is where our border will start. And let's see if I can provoke this bug. Otherwise I'll just isolate it for you. Remember that this is an 8-bit value and we want to wait for hex 12C. So what we'll have to do is write hex 2C, because no more than 8 bits fit in here. What happens then is it should wait for after the last line of display, and we wish to set it to the border color, which was this. And let's try that. That actually worked, but if I comment out these, I comment out the other colors? Oh, I can't provoke it. Alright, if I do this, because, okay, I can't provoke it, but what I was supposed to be showing was a flickering display due to the fact that can I provoke it anyway? Well, let's say for example that we want to wait for the next line, 2D. That is one line below this low edge of the screen. That's not what we wanted. As you can see, it waits first it sets the background color to some middle blue value, then it sets our thin border, and then it resets the background color to hex 112, which was our dark blue background color, and then immediately on the next line it sets the border color. How do we make it wait for? Well, the reason is the 8-bit resolution in here in the vertical position. What you then need to do is insert a wait to ask the chipset to please extend this display beyond the 255th line. This is 255 in hex, and you have to wait for the very last position on this line to tell the system that please, I have a PAL computer, I want the full display, and I want to wait for some rasterline way past what you can fit in the 8-bit value. This worked better. As you can see, it now waits for the for line 255, which is actually about 2 centimeters above the bottom light blue border color. And then it waits for some position below that. And we can correct this now to the actual line below the display, immediately below the display, and wait for the next line and set the medium blue color that we had at the top. So there's only one problem. The CPU doesn't know to reset the background color to our dark blue color. As you can see, it resets it to black, but otherwise the display is fine. So we can quickly change that. Oops. That was the color. Okay, so now seemingly the well, now the display is correct, and we have a nicer display anyway. So what do we need to do next? Well, to understand the raster means essentially, unless you're doing buffering, you need to know when the CPU is. What we want to do is to poke the copper. We want to make another 2 weights. We want to put another 2 weights and moves in this copper to produce the line, and that's basically it. In order to not make it glitch, you could use buffering. You could have 2 coppers and poke the non-active copper and switch coppers, just like you do double buffering. But it helps understanding the raster, and I will show you how to, instead of busy waiting with the CPU, to poke the copper, which can busy wait all it wants. It will still not waste any resources. Okay, let's do this. What do we have here? We have a dynamic vertical position. Let's check that we are at the right position. Okay. It waits for a dynamic position, then it waits and it sets the background color to white. Then it waits to leave that position and set the background color to whatever background color we want. So we need to remove these. I'll cut them out later. And what we should have now, of course, is a completely empty frame loop. It does nothing. And instead, we somehow want this D7 value somewhere in the copper. So we have an 8-bit value here, a vertical weight position, and that should end up in the copper. And furthermore, you want to wait to leave the same vertical position. You can do this two ways. You can add two weights like this. Just for curiosity's sake, I will make them blank. If we wanted this weight, which should set background color to white, and this weight, which should restore the background color, which it already does. If you wanted this somewhere in the middle, you'd just put a medium value in there. Whoops. What the hell? Oh, okay. What happened here was that it changed the background color to white and quickly outside the screen and quickly change it back to the background color. So this is one example way. You have two positions. You wait for a raster position, set the background color, wait for the raster position +1, and reset the background color, just like we did for the thin border. And this is our fixed position raster line. It does not yet move. This section introduces addresses and pointers. We've already used them. For example, the address for the copperlist, which was used here. We put this address in the copper pointer register to tell the custom chips which copper to display. So each frame this value is reloaded. Now we want to put in another address or label, which is just anything with a colon after it is just a label for a position in memory. In other words, an address. So let's call this weight ras1, like we did in the main loop, which we now commented out. And this is the second one. Now this is extra easy. When you poke the copper to do other things, for example, poke sprite pointers or what have you, then you'll or bitplane pointers, then you'll get into adding offsets and so on. But we don't have to do that here. Here, the label before this data declaration statement points to the address of the data that follows it. That means that waitras1 is the position of the very first byte here. So this is, we declare 2 words. These are 2 bytes and these are 2 bytes. So the first of these 4 bytes is the one where we want to change, and the offset to that byte is 0 because it's the first one. So this that means that this address waitras1 points directly to the byte that we want to poke or put a value into. And the same goes for the other raster position. So in the section that we commented out, we should instead type move byte d7, comma, wait ras1. And we can remove this. And similarly, Control B, Control F, Control F. You want to put the same value in wait ras2, but hold on, because the problem with this is the same as before. When we had 80, the position hex 80 in both these bytes, it quickly changed the background color to white and then directly back to the background color. That's not what we want. We want to either wait for the end of the line, or we want to wait for the value in D7 plus 1. The simplest method is to wait for the end of the line and reset the color. Let's see if this has any artifacts. I don't think so. It should merely cut the line off at some point at the right edge. So this makes it safe to put D7 here and D7 here. And we've just replaced our busy wait with 2 instructions. Very nice optimization. This means that after you've poked these, you can add blit awesome bobs and well, what have you, render fractals, and you will have the whole frame to do that in, because you didn't busy wait for whatever vertical position the white line was at. Let's try this. Oops. Okay, that's not right. Let's check that again. It's moving. Let's analyze it. It's moving way too fast and it's too thick. It's like 5 scan lines thick. What I think we have here is the typical empty frame loop problem. When things are moving too fast, and you're doing something simple, of course, then it's due to this main loop being so short, it takes so little time, that it's executed 5 or 6 times in one scan line, and then of course this wait becomes obsolete, so we will have to wait for it to leave that scan line as well. And we can't jump back to this position because it restarts the wait and checks the high bit of the vertical position and so on. So we would have to make a new label, and we will have to wait for it to leave that scan line. Okay, let's check it now. That's strange. Still not correct. It seems to be almost 2 scan lines thick, and it doesn't seem to bounce back upwards. Well, the code is unchanged, so that would be impossible. I would trust the code in this case. So what the problem is, I think, is a typical example of the interaction between different parts of a machine which has the CPU and all its custom chips running at the same time. I think it's a poor coincidence between this position and the fact that directly after that position in the copper list we have this wait. That means that by the time it gets here, the copper may already have read this wait instruction and will obediently wait for the previous frames, vertical position, whatever that is, which will only be lower when it's moving downwards. So that's why it's only showing when it's moving downwards. So if we verify this again, it's only showing when it's moving downwards. When it's moving upwards, the previous frame will have a lower position, and then it will wait out of position, you could say. So that means that, well, the problem is the interaction. Just at the same time that the copper is waiting for the first scan line, we are running this code and changing it. So there's some interference there. So this code only takes like a fourth or a fifth of a scan line to execute. That means that we can just move this waiting position up a few scan lines and be sure that it's executed before the copper encounters or scans to the wait position. And it seemed to work. So this is why it's good to know how the raster works. The copperlist from top to bottom changes the background color to medium blue, then waits for position 2B, makes our little light 1 pixel top border, then sets the background color to dark blue. Then it has two dynamic waits, one which sets the background color to white, and the other which resets it to whatever background color we had. And then we have a wait for FFDF, which extends the frame to a full PAL frame, allowing weights below vertical position 255. And two of those are used here, one for the 1 pixel bottom light blue border, and then one which resets the bottom border color to be the same as the top border color. So that's the execution order from top to bottom for the copper program, and this was the conflicting frame loop, which waited for the same position and poked the copper just as it was executing the next instruction, which was waiting for the dynamic position to set the white background color. And we moved that up a few pixels vertically, and then it had time to poke the copper. If you wish, you could have waited for a high position. You could wait for the last line of a frame, which is hex 37 here, 37 here, and change that to EQ to make the high bit 1 for this wait. So that's the interaction between copper and CPU. And we see a small defect. We would like the scan line to extend fully to the right edge of the screen. We could try the DF position is actually I think the rightmost edge of a full over scan screen, or perhaps 1 or 2 pixels off horizontally from that. It's as close as you get. We could change that to FF and see what happens. Well, better, but not quite. As you see, there are a few pixels missing. So I take that back. The best way to do it is to do it this way, to wait for the 07 position on the next scan line. That ensures that the color change takes effect far outside the left edge of the screen, and ensures that there are no copper shade breaks. So what do we need to change here then? Well, we need to add 1 to D7. The problem with that is it will make the downward movement twice as fast, and that's not what we want. We want to somehow take the current position and add 1 without affecting the current position. We could subtract 1 afterwards, But that's one solution. Let's try it. That works fine, and as you can see, the rasterline is fully extended. I always wanted to say that. Check that out. The rasterline is fully extended. But the alternative is to make a copy. To make a copy of the contents of a register means moving it to another register. Let's take a free one. This is the disadvantage of putting things in registers. You have to remember which ones you've used. So I have to go down here and check, okay, D6 is used for the direction. D4 is used to hold the system copper pointer. D5 is used, well, to hold the interrupt enable bits. So D4, D3 should be free, but you know, I'm going to use a common register to use for temporary storage is D0, so I'll use that. And instead of adding to the current position after that, I will add to the temporary position, and instead of moving the current position into the second wait, I will move this temporary value. That should also work. And the benefit of this is we can add 2 to make it 2 pixels thick. We can add 5 to make it 5 pixels thick. And so on. So have fun with this, and see you in the next episode. We still have the problem that we're busy waiting with the CPU to sync the frame. Now, this is not a problem usually. Usually you don't have a lot of useful things to do while waiting to sync. You sync in order for it not to skip frames and go too fast or too slow and so on. But we will address this in a following episode, and we will still need the sync, but we will get into the vertical blank interrupt. See you then.